Thanks everybody for coming. I'm Erik Erlandson, and I'm the data science team lead at Red Hat's Emerging Technologies Group. And today I'm going to be talking about next generation data science workflows using Ray, or we could just say Jupyter and Ray in the cloud. So today I'm going to be start with basically just describing Ray at a very high altitude, and then I'm going to talk a little bit about some of the other tooling I'm using, Jupyter and Open Data Hub in the context of the talk. I'm going to talk about how you can do Ray with Jupyter using Open Data Hub. In fact, as of now, I'll be describing two ways to do this. I will then demo one of those ways, and once we have that under our belts, I will defend myself as to why I say these are next generation workflows, and then talk about some of the community collaborations that made some of this early work possible, and some of the roadmaps of where we're planning to go from here. So I don't know, how many people here like have worked with Ray or know anything about Ray? Okay, good. Well, I'm glad that I have this overview. So imagine, the space of sort of platforms for parallel computing. Like, over on one end you have tooling like OpenMPI, which offers you, like, obviously very, very fine control over what you're doing, but gives you no real abstractions to work with. So it's like all on you to do all the right things. And at the other end, you have something like, say, Apache Spark, which technically offers you less control in some ways, but also offers you extremely powerful abstractions to get your work done. Ray is aiming to be sort of in between these two things. It wants to give you slightly more flexibility in terms of like the kinds of compute layouts that you actually create, but still has fairly powerful abstractions. It's certainly substantially closer to the Spark end of this spectrum than it actually is something like OpenMPI. So Ray's compute model is actually pretty nice. It's Python native, and so it has two kinds of sort of compute objects. One is tasks, which are just something that you tell it to go do. It does it and returns a result. And then it has actors, which actually function as sort of, durable processes that actually live out on the Ray cluster, like services. And so Ray makes it like extremely easy to do this in Python. If you have a Python function and you annotate it with the Ray remote decorator, then you can turn that into a task. And similarly, if you have a class and annotate it with Ray.remote, you can use it as an actor to like deploy little service-like objects out on the cluster. So I'll give you a brief example here. Let's suppose we want to do the most over-engineered sum of 8 integers ever existed. We can create a little function like I just described earlier called add, annotate it, and all it does is like add 2 integers and return a result. And so you can see here on the left, we can create a bunch of add.remote calls and build up a graph of computations here, and then execute it. Now, if you look at this particular graph, it's actually a tree. I just like to point out, like, while this is a very high-level abstraction, you can actually, this kind of exact topology, you couldn't build this really in something like Spark. It has a slightly different abstraction. So these first few steps here are all declarative, and in this respect, it is very much like a tool like Spark. You're just basically describing a computation that you want it to do, and nothing has happened yet. You're just basically telling the system, here's a setup that you could actually compute. I took this example, by the way, from this very nice blog by Robert Nishihara. Definitely check it out when I post the slides with the link here. And so at the very end, we say ray.get, and at this point, it actually executes something. So again, this is very much, again, in some ways like Spark, where once you set up a computation, if you execute an actual action, Spark knows, okay, now I'm going to unwind all of my graph and compute things and give you a result, and it does this with lazy, deferred execution style. So Ray's core data model is the Plasma object store, and like Python itself, it is basically a typeless store. So you just basically push objects of any type out onto this thing, and they can be pushed around the cluster. Ray likes to do things local first, and so if it has data available to it on one particular working node, it obviously is smart enough not to try to pull that from elsewhere, and so as much as possible, read-write is kept locally. Now, Plasma originally began as an actual Ray code-based component, but since they moved it out to Apache Arrow, so actually you can use it independently on other projects if you wish. Very similarly, Ray's compute scheduling model is local first, and so if it has tasks that it's able to run locally, it will do that, and it will not, try talking to the global Ray scheduler unless it actually needs to get something done. So it's keeping everything local first, obviously, is excellent for overall compute efficiency. Ray comes with some native libraries. There's hyperparameter tuning, RayTune, a reinforcement learning library, RLlib, then just more generically stochastic gradient descent. It has a Ray serve facility for actually doing model serving directly on the cluster. And more recent versions, which is very exciting, has now Ray datasets, which is an abstraction, which is a lot like Spark's data frame concept. So this is actually a nice development, and I'll even be demoing this a little bit later. In addition to native libraries, there are a ton of community integrations, all the popular favorite Python ecosystem tooling. You can see there's a link at the bottom here. If you go there, there's dozens of package integrations now. There's effectively no tool in the Python data science ecosystem that isn't integrating with Ray at this point, as far as I can tell. So, of course, because these are all Python things, that means we can interact with them with something like a Jupyter environment, which in turn gives us the promise of not just Ray, but literate and interactive Ray sessions. And we can take these literate interactive sessions and host them all in a cloud, such as Kubernetes, or what I'll be doing today on OpenShift. Ray is cloud native, and so what do I mean by that? Ray manages all of its clusters via a Ray operator, and so if you want a cluster, you produce a little Ray cluster object, push it up on your cluster, and your Ray operator will then detect it and give you a cluster, and it will not just give you a cluster, it will do a lot of very dynamic scale up and scale down. And as we all know, scaling up is usually pretty easy. Scaling down is actually harder. So it does sort of serverless style kind of computation, almost scale to zero, which is very nice. And of course, once you have a Ray head pod, any client can connect to it. Today, the client in question that I'll be using is Jupyter, but it doesn't have to be that. It can be VS Code or any kind of Python running process. Really, it doesn't even have to be internal to the cluster. You can connect from the outside. So Jupyter obviously can come from a lot of places. The particular source of Jupyter that I'm using is via Red Hat affiliated community Open Data Hub. So Open Data Hub itself is pretty nice. I don't know how many people use or have some familiarity with Open Data Hub? Okay, quite a few more than are familiar with Ray. So, there's some nice things about it. Obviously, it's an open source downstream of Kubeflow, and it serves as an excellent sort of reference platform for doing data science workloads in the cloud. And lastly, it is highly federated, so you can pick and choose what components you want to install, and furthermore, if there's something that it's not providing, it's extremely easy to simply add your own components into the mix, which in fact is how Ray is currently working. It has a lot of tooling. It covers sort of like, in the terms of like data science workflows, it covers everything from business goals to data prep, ETL, model training, all the way out to like deployment, monitoring of intelligent applications. And then like, on the dual axis of personas, it supports, everything from, stakeholders through data engineering, data science, model trainers, and again, all the way to like, DevOps and IT operations. Red Hat actually uses Open Data Hub. We've done a bunch of projects, including things like analysis of OpenShift telemetry for logs, customer support data coming from our systems, and more generalized cluster metric telemetry. So my early thoughts about how to like integrate Ray with ODH started with an analogy, which is that Spark was already supported with ODH, and it works like so. If you're in the Open Data Hub Jupyter Hub launcher, you get to pick an image, and if you pick an image, in this case, specially tagged as being enabled for Spark, then the first thing it does is always spins you a Jupyter environment, but then it will all go out and look for a Spark single user profile. I'll describe a little bit like what that is. But that profile knows how to talk to other data sources for getting templates. These templates are nothing but objects that get created up on the cluster. And so, in this case, the templates tell you how to actually produce a Spark cluster with pods running. And then once you have that, you're in your Jupyter environment and you can connect to it. So you have your own self-service, personalized Spark cluster to mess around with your Jupyter data science. Now, the single user profile and a service template, they're nothing but config maps. So they're just objects containing YAML sitting out on your cluster, which begs the question, what if I wrote Ray profiles and cluster templates that produce one of these Ray cluster resources, and then an operator is living out there and it spins me a Ray cluster. So, spoiler alert, of course, you can do this. Here's a little brief screen grab of one of these user profiles, and you can see what primarily it does is it points to some of these things called resources, which are these template objects. The details, not really important. The main point is there's very unmagical, just YAML constructs that people can program. And likewise, these templates effectively say, hey, here's a template for creating this one of these Ray cluster resources. And you can see there's like little bits of Jinja substitution that you can put in there. And at the bottom, you can see like Ray cluster objects are actually potentially extremely large. It's one of the largest custom resource specs I've ever seen. But you can see the basic flavor of it. And if you do the bit of work to create this, sure enough, you can do Ray on ODH. You can produce, get into the launcher, select a Ray enabled image, and very much like with Spark, it will go off and say, hey, I know how to do that. I can create one of these Ray cluster things, and the operator spins you one up, and you're in Jupyter, and you can talk to it. So you could do this now with current versions of Open Data Hub. In the modern Open Data Hub community parlance, you'd call this probably tier 2. It's not really officially supported, but it's easy to integrate yourself. You could go talk to me and I could show you the GitHub repos where we do this, and it's not a super hard integration with the examples to work with. So, as you can see in the story I just told you, this particular method depends on there being an actual Jupyter Hub launcher that can do all of this. All the current versions of ODH have this and basically work this way. However, in the future roadmap for ODH, the launcher is actually going to be deprecated, and it's slated to eventually be replaced with the notebook controller, which I think is ultimately a good evolution, but it obviously kneecapped, the methodology that I just described, and so I'm not going to lie, for a few weeks I was a little concerned because I wasn't sure where we're going to go with this, but every crisis is an opportunity. And so I started talking with some of my team, and I was like, well, what if instead of making the launcher do this, because we're not even going to have a launcher, what if you just pushed these same YAML objects out straight from your Jupyter environment? What if you could call a function, you could say called a Ray start cluster, and so you're writing your Jupyter and you say start me a cluster, and the pod then just uses the OpenShift API and says, hey, I'm going to make one of these things, and I'm going to push it out into my namespace. And of course, once that's there, the operator, as long as it's running, will immediately detect that and spin a cluster for me. And once it's there, I can again go connect. And so you can see that this is actually simpler. There's slightly fewer moving parts. It doesn't require, it doesn't require a launcher at all. As you can see, the only thing running in here is Jupyter, and as long as you've got the right dependencies installed to talk to the OpenShift API, you could do this from any Jupyter, whatsoever, actually. It further allows us to do some cool tricks. One of the questions we had to answer is, well, if the launcher's not around to tear down our cluster, how do we do that? But, Kubernetes actually makes that easy. There's a thing called owner references. So when I create the Ray cluster, all I got to do is make sure that my Jupyter pod owns the Ray cluster, and what will happen is if your Jupyter environment goes away, you log out or whatever, the pod goes down and the cluster says, oh, here's an owner thing, and it'll delete the Ray cluster custom resource, and the operator will say, oh, the Ray cluster resource went away, and it'll tear down the whole cluster for you. So you're basically getting the Kubernetes control plane to do all the right things for you in a nicely Kubernetes native way. And so that particular methodology is exactly what I'm going to demo today. Basically, I just got this working as of last week. So out here I have, in fact, a Jupyter environment, and I have a little Jupyter notebook here. So this is a live demo. Keep your fingers crossed. So the first thing we do, obviously, like everybody does, we import a bunch of dependencies. I'm going to load some pet data. I just randomly selected one. Looks like maybe a Chihuahua class 10. And I briefly wanted to mention, one of the reasons we're using this data is because it's in fact got a nice new permissive open data license, which is different than an open source license, called the Community Data License Agreement, which is something that was provided to us by the Linux Foundation. I highly recommend, if you have data sources you want to actually make available to a community, that you use a license like this, because there are actually a lot of data licenses people use that would not allow me to use it in this demo today, because there are things like, non-commercial restrictions or stuff like that. So this is kind of like the data version of like Apache open source license. And you can go over to CDLA website via the, again, Linux Foundation and learn more about that. So that's one of my little pet soapbox issues. So anyway, that's the kind of data we're working with. And what we're going to do is we're going to actually do a live training of a neural net pet recognizer. And because this is a live talk, we're going to do it in 2 minutes. So it's going to be basically a very cheesy, low budget pet recognizer. But it is a real... it is a true data science workflow, nevertheless. Hello. Okay, so again, we saw this function earlier. I'm actually going to call the Ray start cluster function. Hopefully it will work. Indeed, it says yes. So one thing about this, which is sort of interesting, is that right now I'm basically driving a lot of this with environment variables. This is work in progress. We want to provide cleaner ways so that you don't have to create yourself a Python.env environment just to make this work, but that is how it's working now. So we do indeed have a cluster, and now we will call Ray init, which is where we actually connect. Oh, interesting. It will be safer if I restart this. I apologize. The bonus extra random animal. Okay, restart the cluster. Yes. Now get a clean. We should get a clean connect. Yes. So it's produced a little context for us. Unlike with Spark, once you've done a Ray init, you don't really have to pass a Spark Ray context around. It does return this. Generally speaking, you don't use them. But anyway, if we go over to our environment here, we can see that there is indeed a Ray cluster running. There's a worker node and a head node. I talked about scale to 0. In practical terms, I generally find it's good to scale down to 1 or maybe 2. So it's this, we have it configured to do a baseline here. Basically, it starts up with 2 nodes for you. So we'll do an auto detect. You can obviously use Torch to figure out if you've got a GPU, and I do not indeed have a GPU on my Jupyter environment. I do have GPUs for the Ray cluster, and I'm going to show you that in a second. So anyway, obviously we're in Torch, and we're going to just set up some basic convolutional network, super small to train fast. And we will stage the same pet data using the Ray dataset stuff that I just described to you. So this is a little bit, Ray likes to make little scary messages like, oh, I caught an exception. Most of them are benign. This is a little bit like, doing a parallelized call in Spark. It's like, I got some data. I want you to produce some, data frame partitions with it. This is the same thing going on in Ray. It's generally very nice. And again, some of this might look a little bit almost PySpark-like. Again, we're doing basically data set pipeline stuff, shuffling and repartitioning. It usually goes relatively fast. Anyway, we just produced 2 separate partitions that are random for your classic train and test data. You can see that up here, I'm going to go over here for a second. These are just not actual data, but they're data set references. So they're referring to stuff that's actually out on the cluster. Sort of like, again, Hadoop-ish or Spark-ish. So now we'll do just some basic functions that are going to tell Torch utilities, how to actually train things and validate things, very classic data science stuff. And so now we are in a position with these functions defined to do a hyperparameter tuning. And because we don't have gobs of time, I'm not exploring a lot of options. I'm going to explore a couple different momentum settings, and I'm going to explore some possible number of epoch trainings. So I'm going to set up one of these little search spaces, and if you do the math, there's 4 possible combinations here. And I will kick this off. You can see here I'm actually asking for GPUs when I do this. So it is now taking each of those 4 combinations and pushing it off to the Ray cluster to do the work in parallel. And you can see it starts off with 1. Everybody else is pending, but relatively quickly it uses the 2. And here's where it starts to scale, because it says, hey, look, I got a load here. Can I get some more actual worker pods? And if I go out and look here, I now have 4. So that's pretty cool. And also sort of similar to Spark, there's a dashboard here. So we also produced, when we spun up the cluster, we also told it how to produce a little service that you can connect to from outside and actually look at the cluster. And you can see that it is using most of the CPUs and a fair amount of the RAM, and you can actually show it's actually using the GPUs as well. So you get basic cluster size and usage statistics. So that's quite nice. Let me go check back here, see how our hyperparameter tuning run is doing. So now you can see it's utilizing 4 nodes, and that's all that I actually could use right now, because I artificially said, well, I know how many GPUs I actually got. It's 4. If you look, still running. So this typically takes a couple minutes to run, and I wanted to show you a few things. However, I thought I would ask if anybody had any questions briefly. You can see some of them have now quit, but I have a minute or 2 while this is grinding away. If I have questions so far, you're welcome to ask. Sure.
Yeah, I saw you're using Operator. Have you looked at the Kubernetes mechanism that's out there yet to do this work?
Right, Kubernetes. It's actually very near on our list of things. That actually is a product of breaking out the operator. But yes, yeah, that's a great point actually. It's like, so I'm using arguably the old style of operator, but they have this Kubernetes thing where the operator used to be literally like in tree with the core of Ray, and they've like broken it out on its own separate Git repo. And so, yes, I was actually talking with Michael Clifford yesterday morning about Kubernetes. That's a good question. So let's see what we got here. Is it all done? It might be all done. Yes, everybody's terminated, so we got some results. And you can see that the thing that I have a hyper tuning run gives you is an analysis, and you can ask it, give me the minimum loss result that you recorded. And so that's this one. And we like to see that the epochs it shows is 200. That's a good sanity check, because you'd like to believe that 200 epochs is going to give you a better loss than 100. So we like to see that. Now, one of the quirks of hyperparameter tuning is, so it went off and like did those runs, but it didn't save any of the results. So once you know what particular hyperparameters you want, you basically go back and do that run. And this time it's going to actually return some weights for us in this mode. Now, one thing you can see here is before we were basically talking to Ray Tune, and now we're basically creating a raw trainer. And so this is just saying, do me an actual neural net training, just one, no hyperparameter or anything. Here's my parameters. Give me your results. And similarly, this is going to take about 130 seconds. And if anybody does actually have further questions, happy to answer them. This is my compromise. It's like the shortest run I could come up with that actually provably does better than random, and not by much. You'll see, but. Sure.
Just another question. Have you played with this in the MIG features when you do have a GPU? Have you done it with the partialized MIG stuff in the operator? So you could like do part of the jobs on one logical segment of the GPUs? Have you done that test yet?
No, I haven't.
Okay.
Yeah, we're treating these pretty homogenously right now.
Okay.
The Ray operator actually has a lot of potential resolution. You can produce different profiles for the nodes it wants, and they don't all have to be the same. Like you could actually have other profiles that just want, ask for nodes that don't have GPUs, or even more intriguingly, its concept of resource was almost a little bit ahead of Kubernetes in terms of like you can define totally arbitrary resource concepts that don't even exist necessarily in the raw kube control plane. I admit I haven't figured out an awesome use case for that, but it might be able to do something like that. Or if you want different GPUs, like I want a particular kind of GPU, I'm pretty sure you could encode that with this. I'm not going to lie, I'm basically happy to have GPUs at all. Yeah.
Supply chain issues, so that's okay.
So let's see, it's getting pretty close.
I have a question for you. You mentioned that looks like that you have used the image data. Have you ever played with the data that is not static, like any dynamic data, for example, data stream?
Are you talking about like an online training?
Online, data is coming, you are doing the training and doing the prediction.
Right. We have not yet. It is one of the things I want to do, some true online training, hook it up to like Kafka, and like actually, do some streaming data. We're also part of this work. Actually, one of the directions we're intending to take it is this is like on a standard, you could call it a data center cluster, but we want to once we have a training workflow, we actually also want to do demonstrating pushing it off to the edge. And the next step after that is actually doing, literally both like training and inference at the edge.
Yep.
We're not there yet, but this was sort of like the baseline we needed.
Yeah, Eric, we do have an example where someone like Audrey's anomaly detection thing does do real-time streaming analysis. So you could use that model development with this. So yeah, so we have an anomaly detection example that uses Kafka streaming as the data ingest. So you could do that kind of finding the needle in the haystack type of use case, and build models off of that for like telemetry from say like a pump or a compressor or something like that.
Yes, we actually want to do this. A lot of the Red Hat telemetry we have access to has that property where some of it's sort of restricted, so it makes it hard to do a talk around. But I would definitely we have a huge backlog of use cases we want to do. But however, again, part of my call to action here is you can set this up yourself if you want to and start playing with it to do your own use cases. That's my real hope. Anyway, we have actual result, and so we can grab that and we can shut down our trainer. So that trainer, I talked about actors earlier. That trainer is basically an actor. It's like sitting out there and you can push things to it. So now I just basically said, okay, I don't need you anymore. we can see what the loss looked like. And indeed, we showed that it had some actual loss, so that's good. So now what we're going to do here is basically we're just saving that model to disk using standard torch-like workflows, and just to show that that worked, we're going to read it back in, and we can see, are we actually getting some results? So here we have somebody's dog, and the label is 36. The predicted, oh, that's the first time I've seen it get one right. So you are privileged. And you're going to see why in a second. So anyway, we can basically just collect the predictions and the original labels and do some obvious basic model evaluations, confusion matrices, and that sort of thing. The first thing we'll do is just get a raw accuracy and compare it to the Cohen's kappa metric, which is one I like because basically this is not a perfectly balanced data set, and so it's always interesting to ask yourself, it's like, well, how good is my model doing compared to just random guessing? And in this case, you can see that a random guess would get around 5%, and I'm just barely doing better than that. So I promised you a low budget neural network, and that's what we got. So we could ask ourselves, well, why is it, you know, how bad is it really? Here's the confusion matrix, and of course, your ideal confusion matrix would be like all the action would be on the diagonal, and you can see this is all over the map. And furthermore, you can see that there's these sort of horizontal bandings, which is very indicative of a learning model that is basically learning to just predict certain classes regardless. And it's the kind of behavior you would expect from a super low budget learning model. It's like, hey, look, you know, you want me to like predict this stuff, I'm going to take some best guesses. If you look at this far right column, it's basically the number of examples of each class. And you can see there's like a lot of dynamic range there, but if you look at the ones that are like in the hundreds, like 170, like class 34, if we go back here to our confusion matrix, it's like, there it is, right? It's like, it's saying, look, I see a lot of those. Well, I'll learn to predict that because you only gave me, you know, 200 epochs. So anyway, that's some basic data science. One last thing I would like to do is take our model and serve it. And Ray also makes this stupidly easy. It's actually kind of fun. I'm doing this in a different notebook. I frankly could have done it in the same notebook, which is part of my story. So here we are again. We're creating a little image model server, and you can see one of the Ray serve decorators at the top, like a specialized version of Ray.remote, essentially. And again, we're asking it to do some GPUs. And in this case, we don't actually have to connect to the cluster or create the cluster because I already created the cluster. But I will connect to it. And here I'm doing another cool thing. If you look down here, it has a runtime environment parameter. You can give it cool stuff like pip installs to do out on the cluster or data. So this is like super easy to push like dependencies out to all the nodes on your cluster. It's a really nice data science user experience there because you don't have to like come to a screeching halt to like recut an image or figure out how to get your dependencies out onto the nodes. It's kind of beautiful. So here we actually have to get raw IP addresses and try to start the server. This particular part could use a little bit of work, frankly. There's literally occasionally some trial and error. I'm pretty sure there's a way to like automate the process of doing this, but We got it. So we're connected. Once you're connected, you can take that little image model process and actually deploy it out onto our cluster. So this is like a server. And if you read one of these random images, there's one, and send it, we get a class back. So we have, in fact, deployed a server all inside of the notebook, and we didn't have to stop anything. We didn't have to do a Flask thing. We just basically said, here, take this torch stuff, serve it for me, and I can push stuff back and forth. And when you're done, you can take the server and shut it down. Oh, yeah, okay, it worked. So that is the demo. And I promised some other stuff here. Didn't save my place. Thanks. So I did want to say, I want to thank a big thank you to Michael Clifford, because he's done a ton of the work modernizing all the original deployments that I did, and got the actual extensions of OpenShift GPU support and Ray GPU support working. He's a member of my team. So I promised I'd defend myself. So now that you've seen all this, what about this do I really think is next gen? Because, of course, you can do all this with existing tooling. So the first thing is, I'm going to go back to this cloud native concept. Again, it has a true cloud native concept of scaling both up and down, using an operator to drive all of it, and clients can connect. It's cloud native in like a way that, earlier tools like Spark or Hadoop never quite achieved, because in fact they were invented before all of the cloud stuff we now have. And specifically having the operator, Spark has an operator, but it's not actually native to the Spark upstream. They're separate projects. So this is like literally in the Ray, the Ray project space, and it's being maintained that way. I think that's actually a nice thing. The other thing is, like you might have seen, I actually used 4 native components in my demo, but it's much bigger than that. Like I said, every tool out there now in the space basically has a Ray integration, and so what it means is you can spin up one Ray cluster and use all these tools plus all of the Ray native tools to do parallelization. And so it's not just unified, it's actually substantially simplified scaling for all of your data science. I think there's a huge potential here for just using this as one unified parallelization engine. I would like to briefly thank the Massachusetts Open Cloud, because we did a lot of the initial deployments in that space, and the Operate First community, which does, basically developing software in the open and extending that with GitOps to doing operating software and services fully in the open. And if you actually look at, you can actually go to GitHub to this day and look at all the original PRs that I produced and all the ones that I've produced since, or that Michael's produced since, to deploy all this stuff. So again, you can learn how to do this using, Operate First's open source repos. Our collaborators at IBM Research are also doing some big things with Ray. They've produced a stack here, which is targeted for using Ray as the engine for doing a lot of big learning model transfer learning applications. We're obviously very interested in working with them. If you're interested in what they're doing, they gave a talk at the recent Ray Summit, which I highly recommend. You get an idea for what they're doing. I have recently heard that there's some people planning to integrate Ray with OpenShift cluster autoscaling. So as your Ray clusters grow, they can actually talk to the OpenShift cluster API and grow, your API cluster in the cloud, which is pretty cool. I was hoping to have better slide for that, but not yet. And lastly, things we want to do. I want to recreate our work with Ray and ODH over on the Mass Open Cloud. Things we've already done, we've got images built using the Project Thoth builds. And as you can see, we have at least a few actual community use cases. Close but not quite done is a formal integration with Open Data Hub upstream. There's actually a pull request for that. And integrating it with the notebook controller. You can see from the demo I have, I think we're very close to having something that will work great with that. I would love to see the Ray operator as a operator catalog offering. And as I said before, we are taking this, we're going to take this stuff and extend it to like deployment, inference, and training at the edge. And at the last summit, Ray Summit, they just announced Ray 2.x, and so we're going to be upgrading all our stuff at some point to that. And that is my talk. Thank you for attending.
Any questions?
I feel like I'm hogging the mic here. Looking at HPC using Ray?
When you say re-architect, when you say traditional HPC, are you talking about sort of like Hadoop class?
No, like old school Fortran, Cray, crusty stuff.
Like the open MPI end of
open,
the scale.
Yeah, MPI. You're not even input. So
that's a great question. I have not seen that. Again, I think to the extent that a lot of things that were written in MPI arguably should have been written using better abstractions, probably yes, but to whatever extent that like somebody is truly making use of like, I need to do something for which there is no abstraction in like Spark or Ray or something like that, then maybe not.
But and one more question. You said autoscaler stuff. Will
Yes.
that be configurable for what the pressure is for growing the cluster? Is it compute, memory, both?
This is a very like nascent project, and in fact, I was asking the people involved if I could even have a slide, and they said we haven't even finished our deck yet. I would assume yes. Most of the autoscalers are doing that. I'm sure it's the way I would want that to work. And you, like you say, you want some pressure thing. It's like you don't necessarily, because obviously cloud spend is expensive, so you don't want it to just like expand your AWS cloud spend just because like somebody spiked the usage necessarily. So yeah,
Have a price guardrail or something.
A price guardrail, or these days, an environmental impact guardrail, or like a CO2 emissions or energy.
ESG.
Yeah, an ESG guardrail.
Y'all are doing some of this.
Is there any plan to integrate with the Hugging Face abstraction layer where you can define the model outside of this and then push it down?
It may already exist. It has an integration with Hugging Face, and I have not played with it, so I cannot claim to know what it does or does not do. But it might. I think it has push down, like the Ray data thing, I think is developing some push down stuff. So hopefully, yes.
And another question, the people that are running already PyTorch and are already running Kubeflow, are you guys seeing any movement of those people into Ray, or how is the industry taking this?
Right. I think that, I don't know, that's a good question. I'm hearing somewhat secondhand customer interest in it. What I have not heard is like specifically who wants to use it and how they want to migrate their workload. Part of the reason for coming here is to hopefully maybe get some interaction about that. I did the first early iterations of this, like a year and a half ago now. And at the time, I just felt like, I could see like there's momentum building, but it certainly, I think, is still a little bit more on the early adopter end of the spectrum. And I wanted, as an emerging tech team lead, I just said we definitely need to have a story around this. But now what I'm hoping is it's grown up enough, and now it's like I said, we're at Ray 2.0. There's clearly momentum built up. I'm expecting increasing customer interactions now. Yeah, thank you. Oh, yes. I will, yeah.